Periodic trends, atomic and ionic radius, and the ionization energy. Okay, so before we get started really talking about specific periodic trends, let's remind ourselves about the effective nuclear charge and the trend that we observe for that. So basically, the effective nuclear charge increases across a period. So what's happening is we're adding units of positive charge in the form of protons, and we're also adding electrons, but they're valence electrons. And valence electrons are not nearly as effective at screening nuclear charge than core electrons are. So we're adding whole units of positive charge, but we're only screening part of it as we go across a period on the periodic table. Now the other thing to remember here when we talk about periodic trends is quantum number n, principal quantum number n. And remember that this quantum number determines the size of the orbital. So the larger the orbital, the farther away on average those outermost electrons are from the nucleus. Okay? And so less positive charge is felt by the electron, and that's simply due to distance. All right? And so just reminding ourselves that n increases down a column, okay? So principal quantum number n, or the size of the orbitals, increase as we go down a column. And remember also that our periodic trends depend on both the effective nuclear charge and also the principal quantum number. And so the effective nuclear charge dominates across a period. So as we go across a period, the effective nuclear charge increases. As we go down a column, then principal quantum number n dominates. So basically the size of the orbitals that dominates the picture. Okay, so atomic radius. All right, so what happens to the atomic radius of various elements as we go down a group? Okay, so going down a group or going down a column, n is increasing. So the orbitals get larger, and this leads to a larger atomic radius as we go down a column. Now, in contrast, as we go across a period, then the effective nuclear charge is increasing, and that leads to an increased attraction for those valence electrons for the nucleus. Okay? And so as we go across a period, the radius actually gets smaller of each of those elements. So starting with, say, lithium and then going all the way to neon, the atomic radius for those elements is going to get smaller and smaller as we go across the periodic table due to this stronger attraction for the nucleus. Okay, so the trend for atomic radius then is the radii decrease across a period and increase going down a group. Okay? All right, so here's a nice little chart showing us the general trends. Actually, these are the atomic radii for various elements, for lots of elements actually. Okay? And so we can see that here on this side of the periodic table, if we look at it from a, each period perspective, the largest ones are on the left side of the periodic table and the smallest ones are on the right, okay, in each individual period. And then also notice that no matter which group we choose, then our atomic radius gets larger as we go down a group, okay? And so let's go over here, even the halogens. So they get larger as we go down a group, okay? And that, remember, that's due to principal quantum number n. All right, so the effective nuclear charge increases across a period, and that contracts the size of the atom. Okay, that stronger attraction draws those electrons in closer and closer, and so the atomic radius is very small by the time you get to the right side of the periodic table where the effective nuclear charge is higher, the highest point, basically, versus any other of the elements in the same period. Okay, so that really high Z effective is what leads to the contracted size. Okay, now ionic radii, those are just a little bit different, okay? And there's two general principles. And basically, the radius of the cation is smaller than the radius of the atom for a given element. Okay? Now think about why that is. Okay? So remember, the cation and the atom are both going to have the same number of protons. All right? But what's different is the cation has less electrons to keep track of. So less electrons to screen other electrons, and you have more positive charge than negative charge, and all of that leads to a contraction in the size. So cations are smaller than the atom of a given element. Okay? Now the exact opposite situation exists for anions. All right? So again, the anion and the atom are going to have the same number of protons. But now the anion has more electrons than the atom. So more electrons to keep track of, and same amount of positive charge, but less attraction for all of those electrons, more screening. And so basically the anion is expanded in size versus the atom. So another trend that we're going to look at is the first ionization energy. Okay? And the first ionization energy is just the amount of energy that is required to remove the first electron from an atom. Okay? Now, technically, this is in its gaseous state, but you can just think about removing electrons from atoms. And basically, it makes sense that as you have an increasing nuclear charge, or effective nuclear charge, which is that attraction of those valence electrons for the nucleus, as that increases, you have to put more and more energy in order to remove an electron. Okay? So the general trend is that the first ionization energy increases with increasing Z effective. Okay? Now, as we go across a period, in general, the first ionization energy increases, but there are little jigs and jags in there where sometimes it's slightly lower than the element preceding it. Okay? We're not going to focus on those exceptions, but they do exist. And the other trend with the first ionization energy is that as the valence electrons get farther and farther away from the nucleus, there's less attraction felt for the nucleus, okay? And so the amount of energy required to take away one of those electrons decreases. So the first ionization energy decreases as valence electrons get farther and farther from the nucleus. And so as we go down a group, then that first ionization energy decreases. Okay, so here is our trend for first ionization energy. So in general, again, not focusing on the jigs and jags, increasing across a period and decreasing down a group. Okay, now, this is a little bit harder. So now we're going to talk about successive ionization energies. And what that means is that you're going to take away the first electron, that's the first ionization energy. But then you're going to remove additional electrons one at a time. And every time you do that, it gets harder and harder to remove an electron due to increased effective nuclear charge. And so you have to put more and more energy in to remove the electrons every time you take one away. Okay, so much more energy is required to remove each successive electron. Okay? So for example, here's aluminum. Okay, so if we put in the amount of energy equal to I1, okay, which is 580 kilojoules per mole, then we can make a mole of aluminum cations with a +1 charge. Okay, so we can remove an electron from aluminum with 580 kilojoules per mole of energy. And that's the first ionization energy. Now look what happens to the second ionization energy. So here's aluminum plus, okay? We're going to put another quantity of energy in, which this time is equal to 1,815 kilojoules per mole. So we're going to start with our aluminum cation. We're going to add in that energy, or we're going to, add that energy to the system and eject or get rid of or, remove another mole of electrons from a mole of aluminum cations. Okay, so aluminum plus I2 is going to give us aluminum 2+ cations now. Okay, and then those electrons that we've removed. So first we put in this much energy to make that cation. Then we put in this much energy to make that cation. Okay? Now what we're going to do is put in another quantity of energy. So we're going to take the cation that we ended up with before, after we removed the second electron. We're going to take that, put in the third ionization energy, okay? And we're going to remove another electron from each aluminum cation, okay? And that's going to cost us 2,740 kilojoules per mole, okay? So again, we put in 580 and we made this cation. We put in 1,815 and we ended up with this cation. We put in another 2,740 and we get this one, all right? Now, look at the fourth ionization energy, okay? Look at this. So now we have aluminum 3+, and this should say I4. So we're going to put in the fourth ionization energy to make an aluminum 4+ cation, and look how much energy it takes. Okay? It takes just tons more energy than the third ionization energy. So what's going on? Okay, so why is that fourth ionization energy for aluminum so high? Okay? So in order to really understand this, we need to look at the electron configurations and look at the orbital that the last electron is being removed from. Okay? So let's take an aluminum atom. All right, and here's the electron configuration for aluminum. All right, now it costs 580 kilojoules per mole to remove this electron from an aluminum atom for a whole mole. Okay, so it's relatively easy to remove. All right. Now, the second and third electrons are also pretty easy to remove. I mean, I know this looks like a lot of energy, and it is increasing as we go to each successive ionization energy, but overall, they're still pretty easy, okay? So if we have aluminum cation, the electron configuration for aluminum +1 is this, and so we're going to be taking away one of these electrons, okay, and it's going to cost us 1,815 kilojoules per mole of electrons removed from a mole of aluminum plus, and that's going to form aluminum 2+, okay? And then if we take aluminum 2+ and do the same thing, okay, now we're going to be taking away this electron, so the one in the 3s, okay? So if we remove that guy, pay our 2,740 kilojoules per mole, then we're going to end up with aluminum 3+, okay? But again, those guys were pretty easy to remove. Now, what happens when we remove the fourth, and where is it coming from? Okay, so look at this electron configuration for aluminum 3+. Okay, that looks an awful lot like the electron configuration for neon, and it is. Okay, so that's 10 electrons, 3 have been removed, aluminum started with 13, now it only has 10, and if we want to remove that fourth electron, not only do we have to deal with the increased effective nuclear charge, but we also are going to have to take away an electron from a noble gas configuration. Okay, so remember, this is the highest effective nuclear charge configuration for a neutral atom, and this one already has 3+. Okay, so we've already taken away 3 electrons, so it's going to cost us a whole lot of energy, 11,600 kilojoules per mole, in order to remove a fourth electron from each aluminum 3+ cation. Okay, so that is a whole lot of energy. And so that big jump, the big jump from 2,740 for I3 versus 11,600 kilojoules per mole, that is where we're going from, you know, just removing an electron from n equals 3, the n equals 3 principal shell. Now we're going to remove it from a noble gas configuration after we've already removed 3 other electrons. And there's going to be a huge jump in energy because of that. Okay? So let's just remind ourselves that periodic trends depend on that effective nuclear charge in N, and the effective nuclear charge dominates across a period, and principal quantum number N dominates down a column. Okay? And so this leads to increasing ionization energy as we go across a period due to that increased effective nuclear charge. And as we go across the period, we're also going to have a decreasing atomic radius. Okay, and that's also due to increasing attraction for the nucleus as we go across a period. And as the orbitals get larger, those orbitals farthest away get larger and larger, n gets larger, we're going to increase our atomic radius, okay, and that's going down a group. And then we're also going to decrease our ionization energy. So if they're farther away, it's going to be easier to take an electron away because they feel less attraction for the nucleus just due to distance. All right, so example problems for this are going to be posted separately, so be sure to take a look for those.